Okay, it's time for us to shed a little light on light. I know, terrible pun. I can't help myself. Anyway, seriously, what is light? I mean, we're all familiar with being in the light or being in the dark. I mean, even babies would understand the difference between light and dark, but what is it? So this is not actually a very simple question, despite the fact that we're always bombarded with a whole bunch of different kinds of light. It has stumped a lot of people for a very, very long time. And so obviously we're not going to give a PhD thesis kind of discussion on what light is, but just to be able to understand a little bit of it. So the first kind of definition that I'm going to give you is probably a little beyond what the course is looking at. So let's talk about what light actually is. It's a movement. Light moves. And it's actually the movement of changing electric and magnetic fields. Through some area of space. So the movement of electric and magnetic fields through space. It was actually more than just electric and magnetic fields moving. It's the light moving in one direction and electric fields oscillating or going up and down in a perpendicular direction to that, and magnetic fields changing, going up and down in a direction that's perpendicular to both of those directions. So this definition is a bit more useful to us, say, in a grade 12 physics class. What we're going to look at here is not so much what light is, but how light behaves. So to that effect, we can say that light behaves like a wave. Well, yeah, usually. Most of the time, it behaves like a wave. But we can also say that light behaves like a particle. That's true sometimes as well, maybe not as easy for us to observe, but it is true, and this is what baffled physicists about light for the longest time. You say, well, is it a wave? Well, maybe, but there's some things that we can't explain if light's a wave. Is it a particle? Well, possibly, but there's a whole bunch of things we can't explain with light as a particle. And so it turns out it's not a wave and it's not a particle, it's light. It's its own kind of little thing. But because it has properties of waves and properties of a particle, we can kind of study the light individually as either being a wave or a particle. In this course, we are going to focus on the wave properties of light. If you are interested in how light can behave like a particle, you want to jump all the way into the grade 12 physics course. So if we're going to talk about light as a wave, I guess our next question is, what is a wave? You've all seen waves, whether it be water waves or doing a wave at a ball game, or even just listening to this video right now, you are getting sound waves in your ear. So the technical definition of what a wave is that it's a transfer of energy. All waves are a transfer of energy. And it's a little bit more thorough than that. It's a transfer of energy through space due to some sort of vibration. We're going to call it a periodic, meaning that it's the same over and over and over again, vibration. Of some sort of source. A wave is a transfer of energy through space due to a periodic vibration of a source. So let's break this down a little bit, and some of the terms maybe that we're not all that familiar with. Energy we're going to kind of leave alone. I think everyone has a basic idea of energy, of what energy is. So that energy could be like gravitational energy through a gravity wave where the particles go up and down in the water. It could be electric and magnetic energy in a light wave. It could be energy of motion or kinetic energy in a wave like an earthquake that you get in an earthquake. So we'll just kind of leave that energy part aside right now and look at this word periodic. And again, the whole idea of periodic means basically reoccurring at regular intervals. So our classes are called periods, and they happen at regular intervals throughout the day. Every hour, the bell rings, you start a new class. You get a little bit of time to travel, but every hour, it's the same thing that goes over and over again. So it's periodic. Our week is periodic. You go Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and then we do it all over again. Our year is periodic. It's the same thing over and over again. The idea of a source, so periodic vibration, anything kind of going back and forth and making something go up and down, whether it be a particle of water or an electric field or air particles in a sound wave. The source is basically what causes the vibration. So what you're hearing right now is caused by a vibration in the speaker in your device, whether it be a set of earbuds or a speaker on your computer. If you were in class listening to this, the source would be the vibration of my vocal cords. That would be true of sound waves. For light waves, there's a whole bunch of things that can cause vibrations, but essentially the vibrations are from electrons in atoms, and that's where the vibration's coming from. That's going to cause light to be emitted. Some of you, through the course of your project later on, will talk about different ways that light can be produced. Some of you may not hit that part, and that's okay. So again, examples of sound or waves. We looked at sound waves. We've looked at light waves. We talked about like earthquakes. Otherwise known as seismic waves. Water waves as well. We get things called gravity waves, which are really weird distortions of space-time that are way, way beyond the level of this course, but are interesting nonetheless. And obviously we're going to focus on light, since this is a light and optics unit. But the same properties that are true of light in terms of how light moves and certain characteristics of the light can also be true of sound waves and earthquakes and water waves and whatnot. So we might have a few questions and details that are going to concern ourselves with all waves and not just light waves. So speaking about those details, as we talked about before, I've actually just answered this. Maybe let me get rid of this part over here. We know what a wave is now. So let's just talk about the characteristics of those waves. So here I have a picture of what a wave might look like. And think of if you're looking at an aquarium from the side and there's a water wave moving from one side of the aquarium to the other, it might look from the side something like this. In which case, you kind of have two axes. Think of this like a graph. Like this axis here would be like a height. This little line right over here, all the way across, would be kind of your rest position, where if the water were to settle out, it would settle out to that position. And this whole axis on this side would be the distance that the wave has traveled. We can also look at this as the left-hand side, this part over here, as being the distance from this middle point, which we'll talk about in a second. And we can look at the x-axis like time. And so if we looked at one individual particle, we say, where is it at a particular point in time? So as time goes on, that particle moves up there and then moves back down to here and then moves up and then moves back down. So there's a couple of different ways of interpreting this graph. So, but a few points we want to make, and I talked about this middle line. What is this middle line? That is what we call the equilibrium. Again, equilibrium. It's the line that the particles will want to go back to. If we have a vibration of particles, the particles want to go back to that middle ground. Like in a water wave, if it were to just, everything were to settle out, that's where they would settle out. And so that's kind of our, think of it like our starting point, where there is zero distance from where the particles want to be to where they actually are. So the wave is at its equilibrium here, and here, and here, and there, and there. All these other points, the particles in the wave are a little bit higher or a little bit lower than they want to be. And again, that could be in a water wave, could be actual height. It could be in an electromagnetic wave. That could be an electric field being a little bit higher than normal or a little bit lower than normal. So a couple of terms that we can show on this diagram. Crests. What a crest is, if you are at all interested in surfing, you've probably heard that term, or you might talk about cresting a mountain. If you're mountain climbing or hiking, it's the top. So right there and there and there, these are all crests. There, there, and the other one at the end as well. So let's look at it as the top of the wave. I put the top in quotation marks because it's not always a physical up or down. Like the vibrations of particles that are hitting your ears in sound waves, they're not actually moving up and down, they're moving side to side. So the crest might be when the particles are all squished together in maximum amount. The opposite to that, which would be the bottom of the wave, is called a trough. Think of kids eating out of a trough. It's like a big bowl, big long bowl if you want to look at it that way. So the bottom over here and over here, those are both troughs. And again, it doesn't have to be a physical bottom. It might be in a water wave, in a sound wave. It might be a part where the particles are spread apart a little bit more. Now we get into some more important terms here. Wavelength. As the name implies, it is the length of one cycle of a wave. So on our diagram over here, we could say from here, from this point right at the beginning, that's not one wavelength. We haven't gone through the whole cycle yet. We've gone up and we come down, but we got to go down to the bottom. We got to keep going. That's our wavelength right there. Notice the symbol I used is the Greek letter lambda. Learn how to write this. The way I write it is basically like if I draw the letter Y and I just put it upside down, there's your lambda. Okay, so it shouldn't be too hard to do one slash and then kind of halfway down another little slash, and that's good enough for lambda. You'll see when you type the letter lambda that comes out a little bit differently. It looks a little bit more fancy, and that's fine, but you don't need to make it that fancy to make it all curvy or anything like that. So notice it, so that's a wavelength from this starting point right to this point over here, but we could also draw a wavelength from here. It would go from that point to that point. We can also draw one from, say, right over here, from there through to here. All of those wavelengths are the exact same distance. It's the length of one wave. Since it's a length, it's measured in meters. Now, some wavelengths are not going to be that big. We're talking about visible light. Its wavelengths will be in hundreds of nanometers. We're measuring in nanometers. You might measure wavelength of a tsunami in tens of kilometers. So it really does depend on the type of wave that we're looking at. The next wave characteristic we're going to talk about is the period. So again, I used the example of classrooms, the class day, and we have a period in your day. It's basically a cycle, one full cycle. So in the period, whichever period you have your science class in, That is one full cycle of a class. You come in, you sit down, the teacher takes attendance, you go through your lesson, and then the bell rings, and then you get to go. The period is how long that takes. So this is the time it takes for one full cycle for the wave to start and then for the wave to end. The amount of time that takes, we use a capital letter T. It's important that when we're supposed to use lowercase letters that we do, and we're supposed to use uppercase letters that we do that. So in this case, it's a time, so we use T, but it's not just a regular time, it's a period, so we use a capital T. And because it's measured in time, it's also, because it's measured in time, it's also measured in seconds. A frequency is like the exact opposite of period. So it's the number of waves or number of cycles in 1 second. So how many of those, now you could probably see that however long the wave takes, whatever the period is, the longer the period is, the less waves you're going to fit into 1 second. So they are what we would call inversely related to each other. The symbol we use is an F. Now in this case I am going to get a little bit fancy and put a tiny little tail on my F, and there's a reason for that. Later on in the course you may come upon a focal length, and that's a different F. So to try to differentiate between the two F's, this one I'm going to draw as what we call a script F by making it a little bit fancy with the tail. And the unit that we use for that is called a hertz, H-E-R-T-Z, with a capital H and a lowercase z. Notice that a little thing, I put a little line on my Z so that I don't accidentally confuse them for 2's. That might be a handy thing for some of you to do if you have writing that is maybe not as neat as it could be. So the frequency is equal to 1 over the period. If the period is 1 second, then you can fit 1 cycle into 1 second. If the period is 2 seconds, then you can only fit half of a cycle into 1 full second. If you think if the frequency is 10 seconds, it means that you can fit 10 cycles into 1 second. So the period, if the frequency is 10 hertz, I should say, and we rearrange this equation, we get T equals 1 over F, same equation, then the period is 1/10 of a second. So it takes 1/10 of a second for one wave, that's the period. How many waves you can cram into 1 second, that's your frequency. The other point that we want to look at in a wave is the amplitude. The amplitude is the height of the wave, and I'll use quotations for height because it might not actually be a physical height. So it's the height of the wave from the equilibrium point, so not from the crest or from the trough, to either the crest or the trough. T-R-O-U-G-H, trough. So back up to my diagram here for a second. In red, this is the amplitude. We're going to give it a symbol of capital A. This is also the amplitude. They are the exact same thing. From there to there, from there to there. Those are all amplitudes. And the amplitude is important because often they tell you how much energy is being carried by the light. It's not the frequency, or generally for a wave, it's not normally about the frequency or period. For most waves, it's about the amplitude. The higher the amplitude, the louder the sound is, or the more intense the earthquake is. Right? So the symbol is A, and it's measured normally in meters, but there are some waves where it could be measured in something a little bit different, but we don't need to worry about that in this class. So that's a little bit about waves in general, and
if you're studying light, you are going to be studying some properties of waves. So this is a little background for you to move forward with.